Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Batrisha binti Abdul Rahim, and I will present about introduction for this experiment, which is vapor compression refrigeration. So, first thing first, this experiment is to investigate the working principles of a vapor compression refrigeration system. And also, there are many parameters that we recorded in this experiment, which is pressure, temperature, and refrigerant flow rate. By doing this experiment, we also can determine the efficiency by calculating the COP, which is coefficient of performance. And in this experiment, we have compressor, condenser, expansion device, and also evaporator. So, the objective of this experiment is to determine the coefficient of performance for vapor compression cooling system. There are two scopes for this experiment, which is the type of refrigerant used is constant, which is R141B, and the mass flow rate for the absolute condenser is between 50 to 10. So we use 50, 40, 30, 20, and lastly 10. So moving on to the theory and working principle. So as you can see there, it states that the cooling system receives the heat from low temperature space and transfer the heat to the high temperature space. This process requires work to be supplied to the system. And also, the formula for the COP is cooling effect divided by work. This figure shows the schematic diagram of a refrigeration system that consists of condenser, compressor, evaporator, and also expansion valve. So at the next picture, you can see that there are two tanks, which is hot tank and cool tank, and supplied by W, which is work.
So for our experimental setup, we've got all our apparatus shown. So all their functions and the related steps will be explained at our methodology.
All right, for the methodology, for the first step is to open the valve for the compressor and condenser. And the second one is to fully open the tap water. All right, for the third step, we set the water flow rate to the evaporator as 25 G per second and water flow rate to condenser as maximum. As you can see from my left or your left, you can see the condenser flow rate controller, and on the right is evaporator flow rate controller. For the fourth step, after doing all the step before, we switch on the main switch. And for the fifth step, we wait for 10 minutes and record all the data from table 3.3.1. So for step 6, we repeat the experiment by using a different condenser flow rate, repeat it for 4 more times. And then after completing the experiment, we switch off the main switch, and then we wait for 1 minute after switching off the main switch, then close the tap water and close the valve that we opened before.
So for results, we've got 5 tests and the data cumulatively for all 5 tests. So first of all, we've got absolute condenser mass flow rate, which I have labeled as M1. The condenser gauge pressure, absolute evaporator mass flow rate, M2, evaporator gauge pressure, compressor power input, and then from temperature 1 to temperature 7, rate of heat transfer of evaporator, Q, rate of heat transfer at condenser, Q, and coefficient of performance, COP. So from the table, to determine the heat transfer of evaporator, and the rate of change of condenser, we can use the formula as shown here, which is for rate of change of heat at evaporator is M1 times Cp of water times the difference between T1 and T2. So as for rate of change of heat at condenser, we've got M2 times with Cp of water times with the difference of T3 to T4. So as you can see for this experiment, we've got a constant which is Cp of water, which is 4.18 kilojoule per kilogram times Celsius.
So we are moving to the discussion part. So for the first question, calculate the rate of heat transfer that occurs in the evaporator and the condenser for the 5 tests run and discuss the result. So this is our formula used in the experiment. Q evaporator equal to M1 times Cp water times T1 minus T2. For the Q condenser, mass flow rate times Cp water times T3 minus T4, and the COP Q evaporator over Q condenser minus Q evaporator. So we already have Cp water, which is 4.18 kilojoule over kilogram Celsius. So for example, we take for the 50 gram per second for the test 1. So using the formula is insert all the values of our data, and we get for the Q evaporator 0.3553 kilowatt, for the Q condenser 0.09405 kilowatt, and then for the COP negative 1.4. So this is the result for the other 4 tests. So for the test 1, 0.36 and 0.09, and moving to the test 2, test 3, test 4, and test 5. So this is all the values for the Q evaporator, Q condenser, and the COP. So as we can see, the rate of heat transfer of evaporator is higher than the condenser heat transfer. Question 2, explain the difference of changing the condenser flow rate of T1 to compressor power. So draw the graph and discuss the result obtained. So the first graph, we can see that all from T1 and from T1 until T4 for all the tests slightly increase and decrease, but sharply decrease on the T5 and then increase drastically until T7. For the second graph, which is compression power input versus flow rate condenser. So initially, as the flow rate of the condenser increased from 10 to 50, the compression power input rises steeply. So this is expected as the system works harder to accommodate higher mass flow rates, increasing the work done by the compressor. So when the condenser flow rate decrease, the compressor power increase because the refrigerant losses heat more slowly. This made the compressor works harder, increasing power input. But at the 40 gram per second, the power stabilizes as the condenser efficiently rejects heat. So after experimenting, for the conclusion, we understand how a vapor compression refrigeration system works and how it transfers heat from the evaporator to the condenser. So the COP, which is coefficient of performance for flow rate 50, 40, 30, 20, and 10 gram per second are negative 1.4, negative 1.7, negative 4, negative 0.2, and 0.16 respectively. So different COP means maybe some error or parallax error happened during the experiment. So contrary to the initial statement, the COP is not inversely proportional to the flow rate. Instead, the COP increases when the flow rate decreases, as seen from the positive COP at lower flow rate. So the compressor power behave differently, as we can see in the graph, because it's increased with the flow rate initially, but eventually stabilize at higher flow rate. This behavior means the system balance heat rejection efficiency and compressor workload. So that's all from me. Thank you.
For the safety procedure, do not touch the compressor while doing the experiment as it will be hot. Be sure to open the tap water and valve before turning on the main switch, and also wait for 1 minute after turning off the main switch before closing the tap water and valves.